Happy holidays! In this lecture, I would like to explain some details about the section ranking population means. Okay, so in these sections, we will actually compare the treatment means, pairwise treatment means for all the possible combinations of pairwise treatment means difference. So let us first talk about the method itself and go through this procedure briefly. So the method is called Tukey's method. And Tukey, in our later slides, I will show you how Tukey look like. And he's actually a very important statistician. So Tukey's method for paired comparison has the following features. The first one is that it is designed to test all pairs of population means simultaneously with an overall error rate of alpha. So here, alpha is also a small number, a small probability that is like a level determined by the statistician or a researcher. And in the textbook, it only very simply say that we would like to control the overall error rate at the level alpha. But in my slides, I add up some more detailed description and explain what the overall error rate means. And in fact, this is called family-wise error rate, and I put more details in the page 48 in these slides. Okay, so alpha is again the Greek letter the same as the significance label, but here it is called overall error rate, and it has a different meaning. Okay, so based on and it is based on a new distribution that is called studentized range. So for studentized range, the basic idea is that it is the difference between the largest sample, the smallest of the k-sample means. So it's a new distribution that is defined basically the difference between these two values, and I will give you more details in our later page. And here we assume that all the sample size for each treatment, I, are equal. And so the idea is that we will calculate a ruler that measures the difference, the distance required between any pair of means to declare a significant difference. So in this section, the Tukey's method is valid only when all the NIs are equal. And NI is the number of observation in treatment I. So this Tukey's method is for the completely randomized design where we had K treatment and each treatment has NI observations. And in our original setting, NI could be different. And the Tukey's method in this section is a simplified version that is only valid when NI are equal. So if the NI are not equal, then you cannot adopt the method directly. So now let's see what's Tukey's method. So the first step is that we will calculate a ruler. And in our notation is use the omega, another Greek letter to indicate the length of the ruler. So the ruler is calculated by a critical value, which is indicated by Q sub alpha and K and degree of freedom, where K is the number of treatment. Degree of freedom is the degree of degree of freedom for the error in the ANOVA table. So the Q sub alpha is the critical value. And this critical value will be checked using table 11 in our textbook. And table 11 is the critical value for the studentized range distribution. So the critical value is based on the studentized range distribution. And again, the next part is S divided by square root of Ni. So S is the common variance estimate calculated from the ANOVA table. So S is the square root of MSE in the ANOVA table of this completely randomized design. Okay, and degree of freedom of error is N minus K, and Ni is the common sample size. So Q is the critical value that we will find its value from table 11 of the textbook. And the rule is that if any pair of means differ by more than omega, this length of a ruler, then they are declared different. Okay, so now let us just show you a simple example first, and then we will give you an explanation why it is true. So let's first implement the procedures here. Okay, so the first one is that we would need to calculate the length of ruler. Okay, so now let's first find the critical value. And the example is the one that we had in the meal plan. So K is 3, and degree of freedom is right now n minus K, where in our meal plan example, n is 12, K is 3. Therefore, the degree of the error is 9. Okay, so our first purpose is to find the critical value, where the critical value relies on two degrees of freedom. The first one is number of treatment. The second one is the degree freedom for the error. Okay, so now let's see how the table look like. Table 11 actually contain 2 pages, and it says that percentage points of studentized range. So this distribution is called studentized range distribution. And the subscript 0.05 is the upper probability. And by default, it's 0.05. So in our example, the K is 3. Therefore, we have to find the column where K equals 3. And degree of freedom is 9. Therefore, we have to go for the row where degree of freedom equals 9. So the critical value in our example here is 3.95. So now let's go back to our example. We have 3 meal plan, and the treatment mean can be calculated directly by dividing their treatment sum. Okay, so to find the omega value, the first one is to find the critical value where it is 3.95 as we just indicated. And here, the textbook slides is very considerate. We have a 3 and 9, so this is 3.95. And the S, which is the common variance estimate, is the MSE from the ANOVA table. So we just find the MSE from the ANOVA table and divide it by the MI, which is 4, and it was given here. So the value of omega equals 5.12, 5.02. Okay, so now our next step is to list the sample means from the smallest to largest. So we had 3 sample means, and we will list them from the smallest to the largest. And omega was calculated, which is 5.02. Okay, so now let's do pairwise subtract. So the first difference is between 9.25 and 13.25. The difference is, how much is that? The difference is 4, which is less than omega. Therefore, we say that there's no significant difference between population mean 1 and population mean 3. Okay. The next one is the difference between the second and the third. So it is now, with very quick my calculation, is 1.5. Therefore, it is still no larger than the omega value. Therefore, we conclude that there is no significant difference between population mean 3 and population mean 2. Okay, and since it's about pairwise, so the last one is from the difference between the first one and the third one. So it's 9.25 and 14.75. So the difference is 5.5, which is larger than omega value. Therefore, we conclude that there is a significant difference between population mean 1, mu1, and population mean 2, mu2. In summary, we can declare a significant difference in average attention spans between no breakfast and light breakfast, but not between the other pairs. Okay, so I will stop this session And I will start a new session that describes the Tukey's method from a more mathematical point of view.